Okay, this is 15.7. 15.7 is on triple integrals with cylindrical coordinates, and you're going to notice that they're really, really similar to polar coordinates. Polar coordinates we had done with double integral. I think that there were actually a couple of the problems that we did in 15.6 that actually turned out to be cylindrical, even though they didn't tell us they were going to be. So that's the good news. So we're going to look at it, and so let's see here, paper review, and so the first thing that I want to look at is just a little bit about cylindrical coordinates. The form of a point in cylindrical coordinates is r theta z. So that's what your triplet would look like for any point. R could be, it's okay for, R needs to be, because it's a radius is what it is. So R needs to be a positive value, just some notes here. R needs to be a positive value. I don't know if it's proper to put equals on infinity, but it just needs to be greater than 0. And so I don't know if I should have just put r is less than infinity on that. Anyway, I'll make fun of myself a little bit. And that was theta, and I wrote q for some reason. I don't know. And so theta is the second coordinate in cylindrical coordinates. And theta needs to be a number between 0 and 2 pi. And then z, like r, is allowed to be anything. Now, r had to be positive. Z can be from negative infinity. I don't really know about the equals there. My lovely friend, she put equals there, so I'm putting equals there too. But z can be anything. Any real number is okay for z. And then this is how you would plot a point in cylindrical coordinates. Is from the x-axis, you would go however much theta, and then r is from the point 0, 0 out to however long, and then z is up, is the deal, and then this is your point that you would have plotted there. If you want, there's a few problems in the book that ask you to plot a few points. You definitely can do that. I'm not very good at plotting any points that go, like if it's pi over 2, then I'm really good at that, because that would just be the y-axis, and and then my r however far up, and then up from there, and but otherwise I'm not the greatest at plotting them. Somewhere I saw that this is straight up and down is a right angle. Where did I see that? And it's not looking like a right angle right here. This is a picture I got out of the book. But I know that it's straight up from that value of r. Where did I see that? That it was indeed, from the book, figure 3, when they plotted a point. And anyway, okay, so then r equals 3. This is where it's kind of nice in cylindrical coordinates, because r equals 3. Remember, I haven't said those yet. Right down here, I have them. I have this upside down, I think, a little bit. This equals x squared plus y squared, and r squared equals x squared plus y squared. And so if you look at what r equals 3 is, I was going to tell you it was a cylinder, because I guess I could reason that out from here. If r was 3, that means theta would be anything from 0 to 2 pi, and z would be any value. And so if you came here and you had something that was r as 3 at any theta value, you can see that if z was equal to 0, that it would just be a circle on the xy plane if z was equal to 0. If z was allowed to be anything, then it would be a cylinder. So I guess I don't need to go into rectangular coordinates to convince you of that. So here I have radius of 3. So coming down here, 3. Coming down here, that's not 3. Every which direction, right? 3. And I'm just trying to draw in, I'm not drawing the same 3. So that is a circle on the xy plane. So this is y, this is x, z, and then it is a cylinder because z can be anything. And so I'm drawing here a cylinder. So that's kind of nice that that r equals 3 is a cylinder of radius 3 is what it is. So it's a cylinder of radius 3. 0 equal 0. Theta equals pi over 4. So pi over 4 is just out in the center between the x-axis and the y-axis. So if theta is pi over 4, that would be halfway. If this is pi over 4, theta equals pi over 4, right? And so that would be halfway. And then any value for the radius going out, remember the radius needs to be positive, so it would be all going out here. So it could be any value for the radius. So this is going to make a, I don't know how to draw it, but a half plane because it's going to go in any z direction as well. And so it's just going to make a half plane going up here. I'm not very good at drawing them. You guys already know that and have done all your laughing. And so I'm going to come here and I'm going to draw this here and I'm going to kind of go up here. And so this is kind of that half plane. And where that half plane, that's the best I can do, where that half plane is going is from the origin out here exactly at pi over 4. So halfway between the x-axis and the y-axis, and any height up and down, right? And any length, and goes on forever. Then z equals 5. So just kind of thinking about z and z equaling 5, that means that up here at a height of 5, I think we already had drawn things like this. It's just a plane, right? And so at a height of 5, I'm just having a plane. So I'm doing my best to come in here and draw this plane in here with a height of 5. So these were parallel to the x-axis, and I'm going to draw this one in here parallel to the y-axis-ish. So there's my plane at z is 5. That's z, this is x, this is y. And then z equals r, and so that means that z and r, so how far you are out and how far you go up is exactly the same for every single point and every single theta. So theta can be anything. And so when these two have to be the same as one another, so how far I go out is exactly how far I go up, what that makes is a cone. And if you don't believe it, I'll show you how it makes a cone. And so our cones kind of look like this. So, and then down this way too. And so, so that is making a cone about the y-axis. If you're wanting, you could square both sides here. So this would be z squared equals r squared. And then remember that r squared equaled x squared plus y squared. So we would get z squared equals x squared plus y squared. And that was the equation of a cone that they give us in chapter, whatever the first chapter we did. Was that chapter 13? So that was one of the things that they had us graph then. So z equals r is just a cone. Anyway, so cylindrical coordinates are kind of nice. You don't have to be able to graph any of these things in order to do the calculus with them. When you're converting back and forth between cylindrical coordinates and rectangular coordinates, going back and forth, x equals r cosine theta, y equals r sine theta, and z just equals z. And r squared equals x squared plus y squared, tangent of theta equals y over x. So this is just like polar, and z equals z. And so so that's kind of nice. We're going to try an example here. So this is example 1. It's asking us to find the triple integral z dv. And so we're going to have some mega volume thing that we're finding. And they've given us where they've enclosed it. This gives us just our bounds, is what this gives us over here. They've already given us the function. And so this over here is just about getting our bounds. And so what would it be easiest to go with? Would it be easiest to try our bounds with z first? Or would it be easiest to try to solve this equation for x, and that one doesn't have x in it, so then what do we do? And so remember, I want an upper bound and I want a lower bound. And so z is the easiest because it's given me what they are. This is either the upper bound or the lower bound for z. And this is either the upper bound or the lower bound for z. All I have to do is figure out which one that it is. So I already know that whatever this mega volume thing is that we're finding here, the triple integral, z, and then instead of dv, I'm going to put dz first. And I haven't decided which one will go first. And so I want you guys to help me decide which one will go first. You can guess at it and then test it to make sure that you're right. Or you can figure it out after you get your picture. So since z equals this and z equals this, and you can draw this if you want. They say it's a paraboloid. And so if you wanted to draw what it kind of looks like, heck, if you draw what it looks like, then you might actually be able to use that drawing that you have in, that's not y, sorry, that's z. You might even be able to use the drawing that you have to figure out what would be on top and what would be on bottom. So z equals x squared plus y squared is going to be some kind of a paraboloid kind of thing going here. And so there it is. And this goes higher and higher, but z equals 4 is a plane, right? And so this is a plane. And so that's where that plane, that z equals 4. And so really, this creates at the top there, we would have that, right? And it's not going to go any higher. So we're looking at where the two intersect, because it's going to be, on the bottom is going to be z equals x squared plus y squared. So down here is going to be z equals x squared plus y squared. I'll show you how to do it if you didn't draw this picture. And then z equals 4 is going to be the upper bound. Z equals 4. And so when you put these together, you always, whenever you have two that are solve for the same variable, you always put them together. So this is going to be 4 equals x squared plus y squared. And it's like, oh, okay, in the xy plane, if I did the projection onto the xy plane, so this is y and this is x, it would be a circle with radius equals to 2, right? Is what it would be. And that's what tells me right there is that I've already got this set up for z going, but as I go to set up x and y, well, you better use polar because you have a circle here. If you don't use polar, now if you were wondering to make sure that you had the right thing, this is my circle there, the projection of this, pick any point. So I'm picking x is 0, y is 0, and put it in here. X squared plus y squared. This is z is 0 to z is 4. And so that's how I know that I have that for sure set up correctly. And so you can't just guess, because if you just guess, you will half the time have it right and half the time have it wrong. But that's how you know, is that this is 0. When I pick the point 0, 0, right, this is going from 0 to 4, and it needs to be in numerical order. Okay, so now what I'm going to do, instead of using x's and y's, because I would have to solve for x and then go from here to here, which would have square roots in it. And it would have square root of 4 minus y squared if I solve for x. So it would be not that pretty. And so I'm going to use that polar, right? And so this is going to be times r dr d theta. And so it becomes the same thing that we kind of were already doing, right? We already kind of did these kind of problems. So r is going from 0. R is 0 to r is 2. And theta is going from 0 to 2 pi. And so this is the mega volume. I'm going to call it MV, mega volume thing. Okay, and so that's what I'm finding here. And so now my choice whether or not I put the z and the r together. And here, when I go here, I don't want to plug in x squared, y squared, because I don't have x squared, y squared here. So I do want to turn x squared, y squared into r squared, right? That's what it is equal to. So when I do my first integral, it's going to be z equals r squared to z equals 4 of z dz. And I'm going to hold the r off, although I told you guys yesterday that when I did one of the problems and I held the r off, I forgot about the r and made the problem a lot easier. So this is going from z equals r squared to z equals 4. So upper bound minus lower bound. Oh, shoot, I got into there. Darn it, darn it, darn it, darn it. I didn't mean to go so far. Okay, so upper bound is 16 over 2, and lower bound is going to be r to the 4th over 2. So this is going to be 8 minus r to the 4th over 2. And then I'm going to do my second integral. So my second integral already has r there, r. And now it has 8 minus r to the 4th over 2, dr. And it's going from r is 0 to r is 2. And so that shouldn't be too bad. And so this is going to be the integral of 8r minus r to the 5th over 2. R is 0 to r is 2. So this is 8r to the 2nd over 2 minus r to the 6th over 12, right? 2 times 6 is 12. And my bounds should go from 0 to r is 2. So when I do that, I'm getting 4 and then 2 squared. I think this is 16. 2 to the 6th, 2 to the 5th, 32. So 64 over 12. I don't remember that number. 64 over 12 is minus 16 over 3. So this is, and then minus 0, right? So 16 over 3, 16 minus 16 over 3 is 32 over 3. Gosh, I did this one and I don't remember those numbers. It's making me worried. And so now my last integral is theta to 0 and theta to 2 pi of 32 over 3 d theta, which is 32 over 3 theta, so at least easy to integrate, from theta equals 0 to theta equals 2 pi. So this is 32 over 3 times 2 pi minus 32 over 3 minus 0. So 64 pi over 3 is my answer there. So we did a nice job on that. If they wanted us to find the volume, so I'll ask you this question, of this figure here, how would you do that? So I've drawn it. What would be different about this example if instead I asked you this paraboloid here, find the volume of that paraboloid? And so how would that be different? I'm going to make sure that I have the right answer on this one because I did it before and I don't remember that being the answer, but it is the answer, so I'm feeling good. So I wish I would have put an example. I wish I would have put an example like that to find the volume of this thing. But all we're going to do is we're just going to set it up. So what if I said to you, find the volume. So this is a new example. I wish I would have put find the volume of the paraboloid z equals x squared plus y squared. I guess find the volume of the paraboloid. That paraboloid, how do I say, I want just the part under the plane of this paraboloid, under the plane z equals 4. We're only going to set it up. So I made a new example. Find the volume of the paraboloid. So that means to find the volume, we're going to be integrating 1, right? So that's how you would find the volume. You integrate, you let your function be 1. So that's how it would be different. And it would still be dz and then r dr d theta, where z was going from r squared to 4, and r was going from 0 to 2, and theta is going from 0 to 2 pi. So that would be the setup there. And of course, if someone asked you just to set it up, you could say 1 times r is r and have written this volume as this triple integral r dz dr d theta. And that's the order that you do them in when you have these. So there was triple integrals that they had in the triple integral section that were essentially the same thing. Instead of having z first, you could have whatever variable first. And then they called those polar-like is what they called. And so I guess if you have z being z and then it's more uniquely cylindrical. And anyway, so that would be kind of that story. So to find this volume of this figure right here, where this is that plane 4 kind of cuts it off, find the volume of that. That's how you would do that. And this was the mega volume thing, because it's this thing that we have found here is in 4 dimensions. So kind of odd. Okay, so that's kind of the story on that situation. We kind of already did. I kind of feel like we did them in the cylindrical ones anyway. Anyway, so give a try to those, and that's the end of this recording. I won't make it longer by trying to come up with another example.